Hi, everyone. Welcome to BCast, which is a bi-weekly series of talks given by industry and academic leaders in the field of high-performance computing, which is organized by the Scalable Parallel Computing Laboratory led by Professor Thorsten Heffler at ETH Zurich. Today, we have Sudeep Bhoja, who is the co-founder and CTO of D-Matrix, focused on generative AI inference accelerators using in-memory computing, chiplets, and scale-out interconnects. Previously, he was Chief Technology Officer at the Data Center Business Unit at Infill Marvell. He also was a Technical Director in the Infrastructure and Networking Group at Broadcom and a Chief Architect of a startup, BERT Networks. He's named inventor of over 40 pending and approved patents. Sudeep, today we'll talk about a chiplet-based generative inference architecture with block floating data types. We will start with his presentation, and afterwards we will have time for questions, so please save those for a Q&A session. So without further ado, the stage is all yours, Sudeep.
Thank you very much, Marcin. It's a pleasure to talk to you all. So I'm going to talk about a chiplet-based generative inference architecture with block floating point data types, along with my co-authors. A overview of the talk around our architecture. We'll start with that, and then Ilya is going to talk about numerical accuracy analysis with block floating point data type, as well as with the GPTQ algorithms, and then we've done some work with optimizations around KV cache using L-attention, and so Ilya is going to talk about that. Satyam and Shane are going to talk about the spatial architectures and ML tools. So this is a picture of our Corsair 8 chiplets, and so we have 8 chiplets. Each of the chiplets have access to 2 LPDDR channels, and all of those chiplets are connected using an all-to-all interconnect. The first 4 of them are shown here, 1, 2, 6, and 5. They have a BOW-based all-to-all interconnect. The problem we're trying to solve is GPT model inference. So in GPT model inference, the autoregressive token generation requires very high memory bandwidth during inference. And the main reason for that is the decoder loops in the transformer have very low arithmetic intensity. So if you have a beam of 1, you only have 1 multiply accumulate for every weight fetch. So you have a model that exhibits a very, very low arithmetic intensity. So the model becomes memory bound. Also, you have a KV cache for the context for every user, and that has to be fetched. Even if you batch it, you need to fetch them per user, and that can contribute significantly to the size of the model. And there are strict latency constraints and the KV cache that discourage high batch sizes. So that the standard techniques you can use in training may not apply in inference because there are strict latency constraints. So, for example, in GitHub Copilot Codex, you have potentially 500 tokens being generated, and if each token takes 10 milliseconds, then that's about 5 seconds of user latency. So these user-facing latencies constrain the batch sizes that one can use. And finally, the prompts that are provided for the decoder models, tend to be fairly long, and there is an increasing move towards higher prompt sizes, going from 512 prompt size to more recently 32K, and that requires very high intensity prompt processing. So you have this problem of both memory bandwidth, memory capacity, high compute, and it's a very difficult problem to solve. So here's one potential solution to this. We are using chiplets to break up the model. So we put 8 chiplets to break the radical limit. And so we can also get high memory capacity on on-chip SRAM. So in this architecture, we are showing 2 gigabytes of SRAM, significantly higher than modern GPUs, as well as very high memory bandwidth through its internal SRAM architecture. So we get 200 terabytes per second memory bandwidth compared to HBM memory, which chips today do about 2 to 3 terabytes per second. So 2 orders of magnitude higher memory bandwidth. We have significantly high, throughput, 3.2 petaops to 12.8 petaops, depending on our data types. We'll get into that in a moment. So that helps with prompt processing and in general provides for high compute throughput. So we want to make this chiplets look like a monolithic chip. So it's very important to get efficient chiplet to chiplet, or what we call die to die interconnect. And so we're using something from Open Compute called bunch of wires interface, and that allows us to get 8 terabytes per second and make these chiplets look like a monolithic chip. And finally, each of these cards have to be connected together in a scale-out manner on what is called the universal baseboard, and that allows us to connect many cards together, and for that we have 512 gigabytes per second of PCIe bandwidth. So each of those chiplets are connected to LPDDR chips. Those are the black chips shown in the picture here. So we have very large prompt caches that we can support in DRAM, and then we have prefix matching algorithms to cache the prompts from DRAM. So in this case, because of our use of LPDDR memory, we get very high capacity, 256 gigabytes of DRAM, compared to modern GPUs that have 80 gigabytes of HBM memory. And finally, we need to be able to scale out the all reduce among all of these chiplets and cards, and that tends to become a bottleneck. The model becomes communication latency and bandwidth bound, so we need techniques to improve that all reduce communication time. So here is another picture of our die-to-die interconnect. So between each chiplets, we use a clock forwarded architecture, and this is a test chip, 6 nanometer TSMC test chip. The die-to-die interconnect looks very different from a SerDes links. We don't do clock data recovery. We send the clock and parallel wires on these links. Because of that, the power consumption of this link is very low. We can get to half a picojoule per bit compared to 5 picojoules per bit or larger with chip-to-chip links. And a ball map of this is shown on the right. There are 16 channels with a clock that is forwarded, a differential clock, and all of the data lanes are single-ended. And we also have forward error correction because it's a very latency sensitive link, and we don't want to do much retransmission. We have FEC to protect these links. So a test chip picture is shown below. In the test chip, there are 2 dies in the test chip, and there are three links, 3 millimeters. That's a straight link there, and then there's 2 other links that are 15 and 25 millimeter, and certain measurements are shown in the picture here, and you can see that there is a significant amount of eye opening, which is shown in the right hand in the green picture here, that allows us to achieve error-free operation PRBS31 data transmission across these chiplets. So the intent here is to make all of these 8 chiplets look like a monolithic chip. So I'm going to get into the details of the chiplet in a moment. So this is each chiplet. So there's 8 copies of that inside that package. The chiplet has this notion of quadrants. So there are 4 quadrants here. The quadrants have compute cores, which are these in-memory compute cores. The compute cores, each of the compute cores have what is called the digital in-memory compute matrix multipliers. Each of these matrix multipliers can do a 64 by 64 block floating point 16 matrix multiplies. So there's 8 of them. So you can complete a 512 by 64 matrix multiplier. The idea behind the digital in-memory compute is that we co-locate compute and memory together. So the way we do that is we take a 60 SRAM bit cell and we add 4 transistors to make that a multiplying element. Unlike a traditional SRAM, we activate all of the word lines at the same time. So all the 64 word lines are activated, and we have a huge number of columns here that all parallelly can perform the matrix multiply in single shot at very high bandwidth. So because of the number of parallel multipliers, we can reduce the clock frequency of the digital in-memory compute engine and get to very high energy efficiencies. This is a measured result in the same TSMC 6 nanometer test chip. We get to 40 TOPS per watt in a block floating point 16 data type. And because the DIMC operates in a bit serial manner, so it's very easy to reduce the precision to 4 bits, which is the block floating point 12 data type, and there we can get to 150 TOPS per watt. So that's some details about the DIMC. In addition to the DIMC, we have a 4-slot vector SIMD engine. And the activations are stored in this memory called the global memory, and that activations can be multicast to all the cores and the slices. There are 4 slices inside one quadrant that are interconnected through a all-to-all network on chip, and the network on chip supports multicast across all these cores, and the control plane for this quad is a RISC-V engine with a dispatch engine that is attached to that. So in addition to these quads, we have quite a lot of I/O here. There's a PCI Gen 5 X16 I/O, and then the 2 channels of LPDDR that I talked about, as well as 1 terabyte per second, 8 terabits of die-to-die bandwidth to connect these chiplets together. So we support these block floating point 16 and block floating point 12 data types that I will describe in a moment in more detail. But we also support a standard 16-bit data types, bfloat 16, FP16, and FP8, as well as integer data types. And some of the metrics for the chiplets are shown here. Each of the chiplets can offer 25 terabytes per second of SRAM bandwidth and 256 megabyte of capacity. So when we scale it up, we get to 200 terabytes per second. So some additional details here about block floating point. So in regular floating point, we have every 16-bit element has an exponent and a mantissa. But in block floating point, we share that exponent across n values. N can be 16 or 64, depending on the size of your block. And so the BFP 16-N format is shown in the middle. And in the BFP 12 format, we retain the size of the exponent to be 8 bits. And that's it. In our case, it's a floating point number, an FPA type of number, and then we have 4-bit mantisas for the block floating point 12 arithmetic data type. So the key here is that we have, we use these in-memory compute cores to provide the low precision integer mantissa, and they have a wrapper around them that allows for shared exponents. So a matrix vector example is shown here, where the global memory or the input buffer holds activations that are then streamed into the DIMC. The orange boxes here are the mantissas. The green is the exponent that's multiplied with the weights that are in each column, and you end up with a 30-bit data type that can be accumulated, and the accumulation is done in hardware. So the 8 IMCs can then provide a 512 by 64 matrix multiply, and that is stored as a 32-bit floating point format in a buffer that is next to the in-memory compute elements, and then the SIMD operates on them with a 16-bit float data type, and all of the quantization is done in hardware on the fly. And we'll describe GPTQ algorithms for compression of weights to these formats. And in our inline decompression, we use a format called SBFP12, which Ilya will describe in a moment, which has a 4-bit mantissa, a 16-bit block size, and 8-bit shared exponent. So Ilya, you want to?
Yeah, thank you. You can hear me, right?
Yes.
Yeah, so I'll follow up on Sudeep's introduction of block floating point format, and we will describe a little bit our findings on accuracy of this format, both some theoretical aspects and empirical analysis. This has been published in this paper, so this is a header of the paper that can be found on the archive. So can you go to the next one? Yeah, I can't. Yeah. So a little piece of justification for BFP can be seen on the left here. The idea of sharing an exponent can be thought of in the following way. So we know, for example, that we know that in many deep networks, we train the weights starting from some random initialization, for example, Gaussian. So on the left here, we can see a couple of examples of weights in some layers of deep networks and their kind of evolution, how they change during the epochs of training. And we see that pretty often the weights don't spread out very widely. They're pretty much concentrated around the origin, which kind of suggests that our numbers that we want to quantize, they share very close ranges or exponents. And in this in this paper and in our approach, we're going to analyze the precision, the accuracy of the results of inner product. So as Sudeep said, BFP format, block floating point format, is very kind of useful in specifically in matrix multiplications. Here you can see in the picture, we have a row vector and the column vector that we multiply, we compute the inner product, which boils down effectively into summing up the exponents, and then integer multiplication of the row and column. So effectively, the computational complexity is like integer inner product, but we get the benefit of a larger dynamic range thanks to our exponents. At the bottom, you can see an example of multiplying two matrices. So the left one, we need to quantize row-wise, which means that we will block the rows of this matrix into our BFP format. But the right metrics, the right operand, we will need to quantize column-wise. This way, we can later multiply, like apply our inner product, like in the top picture. We will multiply the rows by the columns. Yeah, next slide. Yeah, so a few things we can choose as the designers of this format that we are going to apply. For example, we can choose the block size, which is the number of elements in our column or row that we are going to quantize at once. They will share one exponent. Another thing we can choose is the precision format. How many bits do we allocate for every mantissa, for every number in the block? We can also choose the format of the exponent. So in this work, we will be talking about how to choose the blocking size, the number of elements in every block. If, for example, we have chosen their precision to be, let's say, 8 bits or 4 bits. So here you can see that the popular choices of formats that we are using usually are what we call BFP 1664, meaning that we allocate 16 bits for the exponent plus mantissa, 8-bit exponent and 8-bit mantissa, and BFP 12, which is 4-bit mantissa and 8-bit exponent, and here the block size is 128. So in the next slides, we will try to justify these choices. Next slide. Yeah. So to build up our theoretical framework, let's introduce another auxiliary format that will later also serve as a standalone format. But for now, it will help us do the analysis. And we call it scaled BFP. So here, so in the original BFP, we store the exponents as integers, and then the scaling factors of every block becomes power of 2. So how we compute the numbers after quantization, we take the mantissas and we multiply them by the 2 to the power of the exponent. Those are the numbers that we can recover from the format. In SBFP, instead of storing the scaling factors of the blocks as powers of 2, we will store them as just, let's say, FP32 or FP16 high precision numbers. This will help us build up the analysis. So you can see here on the right a comparison of BFP and SBFP. So in BFP, again, like we store only the exponents and then we compute the scalars as powers of 2. And in SBFP, we compute the scalars themselves. Next slide. Yeah. And here is kind of our theoretical framework. So again, on the left, you can see justification for assuming that, for example, we can take the weights to be Gaussian, and that will be our kind of theoretical assumption. We will assume the weights are Gaussian distributed. Later, we can remove this assumption, but just to simplify the analysis, for now, the weights will be Gaussian, let's say, independent with some standard deviation sigma. And what we're going to do, we're going to take 2 blocks, a row block and a column block, and compute their inner product. This inner product we will analyze for the accuracy of quantization. So the bottom row shows the error of that we are going to look at. It's the difference of the initial inner product of our initial vectors x1 and x2 minus their quantized versions. So in the quantized version, what we have the rounded mantissas inside the sum multiplied by this scaling factors of 2 blocks, which are y1 and y2. Alpha 1 and alpha 2 are just scalings that we need for binary quantization. Okay, so at the end, we see that we need to analyze the product of y1, y2, which are the scaling vectors of the blocks. And inside the square brackets, we have the difference between the quantized mantissas and their kind of initial values. Yeah, next. Yeah, and so here, the scaling factors are, of course, determined by the maximal amplitude inside the block, the absolute value of the maximal number. So here, we can talk a little bit about how we determine the statistics of the scaling factors of the blocks. I'll not go too much into detail because we don't have too much time, but in very kind of coarse terms, we can show that, first of all, we know pretty well the behavior of the scalings of the blocks because we have assumed that the elements of the blocks are normally distributed. So we know that the expected values of the scaling factors are proportional to the square root of log n, where n is the size of the block. But we also know that they will be very sharply concentrated around these average values. So you can see that the variance of yn of the scaling factor is decreasing with n, which means that they will be very sharply concentrated if the block sizes are large. Yeah, next slide. Yeah, so here, let's illustrate this idea again. We can see at the top the pictorial kind of form of the distribution. We sample our numbers from x1 to xn from this distribution. You can see them on the x-axis. Then we need to determine the maximal number that will give us the scaling of the block. So in SBFP format, the scaling is determined by the maximal value. And in BFP format, we will need to take the closest power of 2 on the right. You can see at the bottom these bell-shaped curves. They show us how the scaling factors, the scalings of the blocks, how they concentrate around their mean. You can see that for small number of elements and one small size of the block, the bell shape is wider. So here, our maximal elements, or like the scalings of the blocks, they are a little bit more widespread than when the block size grows. So you can see, for example, for N2 and N3 block sizes, the scaling factors concentrate much more sharply. And here we want to distinguish two situations. For N1, when the block size is close to the power of 2 on the left, we will need to round our scalings to the closest power of 2 on the right, to 2 to the power k plus 1, which means that we will lose a lot of precision. Our scaling factors will be around the bell shape of N2, while in BFP, we will need to round them, the mantissa up to the closest power of 2. So this is the source of the loss of accuracy. Next slide. So in our paper, we have a few theoretical results. I'll not go too much into detail here because of lack of time. Yeah, you can look it up in the paper. We will just next describe a little bit the results. Yeah, next slide. So here we show the comparison of the empirical analysis to our theoretical bounds on the left for SBFP and on the right for BFP. So the theoretical curve here coming up like from the theorems, like propositions we showed in the previous slide, the green ones, the green curves. We also developed asymptotic bounds, the orange ones, but here I'll not talk about them. We need to compare the green ones to the blue ones. So the blue ones are the theoretical, empirical results from simulated Gaussian distribution, and at the bottom, comparison to some real data, real weights taken from GPT-2 XL network. And you can see that in both cases, for SBFP and BFP, the empirical results are very close to theoretically predicted. You can also see that the shapes in SBFP and BFP cases are significantly different. That's because in BFP, exactly as we explained it before, we need to round up the scaling factor to the closest power of 2. And in those cases where scaling factor is far from the nearest power of 2, we lose much more accuracy than when we are close to the power of 2. And in the next slide, we will use the analysis of SBFP to show that we can choose some optimal parameters for BFP. So here we do the following. We compare the variance of the BFP error to the variance of SBFP error. We divide these two variances and look at their ratio as a function of mantissa precision and the block size. So if we fix the mantissa precision, here we see that as a function of block size, our ratios, the ratios of variances, will have optima. And for example, for mantissa lengths of 4, p equals 4, we see on the left that this curve, the orange curve, reaches extremum. It reaches a minimum somewhere between 64 and 128. So this means that our predicted error will be the smallest relative to SBFP format, somewhere between 64 and 128. And these are exactly the sizes we are using in our design. And on the right, you can see the comparison of these theoretical curves to the empirical ones in the same GPT-2 Excel. Yeah, so next we will talk about GPTQ. Yeah, if there are any questions at the end, we will be happy to discuss. So next, I'll say a few words about the application of GPTQ, like the friendship between GPTQ and BFP format. So this is the paper which is probably like everybody in this audience knows about. So yeah, in the next slide, we can see the idea of GPTQ quantization. Next slide. Yeah. So on the left here, we can see the original algorithm of GPTQ, which I'll briefly discuss in the picture. I'll explain it in the picture. So what we do is basically the following. Here we see the matrix of weights that we are going to quantize column-wise based on some calibration set of activations that we have. I'll not go very much deep into the algorithm because I just have a few minutes, but the kind of the idea of implementation is that given some what we call here Hessian matrix, which is computed from the calibration data, what we are going to do is this. We will split our weight matrix into these blocks. So here we have 5 large blocks, and inside every block, we will quantize it column by column, and then propagate the errors of the column quantization all the way to the right, like to all the following columns in the block. Then when we finish quantizing the block, we will propagate the error to all the other blocks on the right. So in our work, we adopted this algorithm to BFP. And this can be easily done if we think of BFP as a block format across the columns. So for example, let's take the middle block here and assume that we have 64 columns in it. So instead of quantizing every column, what we will do, we will quantize all this block at once and propagate, and again, like in the initial algorithm, propagate the error all the way to the right through the other green blocks. And we saw in our experimental results, in the next slide, that this actually gives a pretty good result. And it also saves us some compute because we don't need to quantize inside the blocks column-wise. We do it a block at a time. So here you can see the comparison of the results reported in the paper in the red table to what we got on 3 data sets for OPT family of networks. We have more precise kind of tabular representation, but here you can see in graphical format that we converge very close to the original accuracy with SBFP format. So here, a few details. SBFP format that we mentioned here is like the one introduced before, where the exponents are in FP8 format. And we need to fix some parameters of this format, for example, exponential bias. So here it was 12. I don't want to waste too much time. If anybody has questions, we can discuss it at the end. So here the block size was 64, and we used SBFP with scalar format of FP8, and the block and the mantissa width was 4. So here every mantissa was allocated 4 bits. Yeah, so next, I just have a couple more slides. Yeah, about EL attention. So EL attention is another paper that we were kind of building upon to improve the performance of Corsair. So here we will talk a little bit about the cache. Next slide. Yeah, so in this paper, the authors suggested the following usage of the following optimization of KV cache. So we know that in every attention block, we first need to compute our 3 vectors or matrices Q, K, and V. Q is the query that renews on every autoregressive pass of the GPT like generators, GPT networks. So Q we do not store; it is new. But K and V we want whether to recompute or store from the previous autoregressive stages, or from, let's say, processing the prompt. So the basic way of doing it is just to store keys and values themselves in the cache. So instead, the authors of the EL attention paper, they suggest to store the input vector to every decoder block. It's this blue column on the left. And on every pass, we can rematerialize K and V by just multiplying this input vector by matrices WK and WV. So we store the input and we compute K and keys and values on every pass. So what we suggest instead is to store the keys and compute only only values from the keys. This way, yeah, the next slide. So this way, we save, we reduce the amount of compute by 2. So you can see on the left, the original suggestion is to compute K and V on every pass from what is cached from the inputs. And on the right, you can see how much you save if you compute just values from keys. The matrix that we need to use in this case is already, of course, a different one. It's the inverse of WK multiplied by WV. But the kind of, to our benefit, this matrix is, all these matrices, all these projectors are always invertible. So there are no numerical issues with computing this product, but it saves us half of the compute on every pass with the same amount of cache. Yeah, that's all. Thank you.
All right. Thanks, Ilya. I'm going to talk a little bit about one of the challenges that we have with any new architecture, especially when you're talking about these gigantic models and equally complex spatial architectures on which those are meant to be executed. One of the problems in the backend compiler is how do you optimally map pieces of workload to the specific regions of the chip in a problem known as compute memory mapping. So this is a work done by the 4 of us listed here. Tristan was one of our fall interns. So this is a research project which was largely driven by as an intern project, but we are continuing to work on it towards production. Next slide. Okay. I'll go a little quicker because we're up against the clock. If we look at the figure, the problem of mapping is described using 3 or 4 different parameters. The inputs coming into the mapper, which is the center of this picture. On the left, you have the graph represented as a set of compute tasks. Those are arranged in a temporal manner. There are dependencies between them. We'll talk a little bit more about that. And on the middle, top middle, you have the hardware resources, which is mostly, in our case, a spatial architecture, although you do allow reusing them. So it's not as restrictive as an FPGA or a truly spatial only architecture. We have a spatial temporal computational paradigm. And then you have a set of constraints which limit how much flexibility you have, how many functional constraints you have. Those feed into the mapping algorithm, and it generates a spatiotemporal resource-bound schedule of execution that gets lowered onto the hardware for execution. And then this process results or is governed by what metrics are important to us. Some of the metrics include throughput and utilization, which we would want to increase or maximize, and others such as energy consumption or the interaction with the control plane that you would want to minimize. So we will talk about mapper, generally speaking, as a combination of 3 steps, which is partitioning, partitioning onto set size of compute graphs, mapping, which is resource mapping, and scheduling, which is further taking that mapped compute graph into a schedule of execution. So the inputs, and next slide. We will now look at it as an optimization problem. Now that we know the inputs and the parameters coming in and the kind of outputs expected, there are 3 problems, the 3 components in casting this as a general optimization problem for which we want to achieve a certain optima. You need a cost model or an evaluation function that's going to determine how good or bad a particular mapping is. On the right-hand side, you would need some heuristics that can give you insights into how do you get to those heuristics, or how to utilize the constraints that you have internally. And in the middle, which is the center of this talk, is the solver or the methods that we would use to perform a search in the solution space based on the cost model that helps us get closer to the optima. So this is represented in a pictorial form on the right-hand side, where we take the workload, which is a temporal graph, and the hardware configuration as input, and feed it into a mapper. That generates a mapping, which gets fed into what is known, represented here as SOL, or a suite-applied model of the hardware architecture. That generates a goodness of the metric, which gets fed into a solver, and that feeds back into the mapper. So how do we best solve this problem of generating a new mapping corresponding to the feedback that we are getting from the cost function? There are many ways to do it. There are optimizations such as integer programming or Boolean satisfiability formulations. The problem with each of them is that for a new model that comes in that you have to compile, you have to apply the iterations again and again. There is very little portability. If you have to achieve an iterative minimum on an integer programming problem, you basically have to do all the iterations again. What we came up with is the potential for utilizing reinforcement learning, in which case, next slide, please. In which case, you can cast this as a gaming problem, or a problem to be solved by an agent which is trained on a bunch of iterations of the model mapping. But then at compile time, you don't have to retrain the agent. The agent by now would have already learned the best known techniques to converge towards to an optimum. And therefore, you're basically doing quote unquote inference at compile time. So that's the premise. It allows us to have a limit on the compile time, the ability to handle very large models, very large generic models, and still get the goodness that we would otherwise not get if we go strictly heuristic. So how do we cast it as a reinforcement learning problem? The 2 main areas that we have to understand a little in detail is the state space and the actions. So for us, the component of the state space consists of the directed graph, which consists of the instruction set of our architecture. So these are a level below the ML level operations that typically form an ML graph. These are lowered down to the instruction set, and the edges specify dependencies. So these could be node level functional dependencies, or this could be resource level dependencies. Both are captured using the edges in the graph. And then we have a set of resources, which are provided as hardware configuration information. And then G is the mapping that provides us the pairing of these resources. And we do acknowledge the fact that we may have to utilize the same resource multiple times in order to satisfy the requirements of a given graph. On the right-hand side, we have the action space. Here, we take two types of actions. And I think, Sudeep, you have to click one more time. There. The two types of actions include swapping and assignment, direct assignment. What that means is that given a neighborhood around a particular node, we may be able to swap the assignment between one of the neighbors, or we may be able to do a direct assignment within that neighborhood. And the illustration of neighborhood is shown on the bottom, where the green core is the one for which the node is being reassigned, and the four pink or red circles indicate the neighborhood of that. Now, this is possible for us to do because of the spatial nature of our architecture. So we can visualize the resource map as a 2D grid on which we draw an arbitrary boundary. And within those boundary of defining the neighborhood, you can apply these swapping or assignment actions. One other thing that we do is we prevent certain actions by action masking. And this allows us to put kind of constraints on the size of the search space. So as you can imagine, for a very large graph and very large computational architecture, this is an intractable problem to solve, which is why we are looking at solvers in the first place. The few ways in which we are putting constraints on the growth of this problem is by partitioning, by action masking, by limiting the neighborhood size, and so on. That does prevent, in some ways, the exploration of the solution space by the agent, but it allows us to converge somewhat faster. So it's a reasonable compromise, and it already gives us good results, which we will see shortly. Next slide. The final part of the RL formulation is the reward function. And this is super important. So we take two types of reward metrics. One is the latency and one is congestion. Now, if you recall the figure that we showed earlier, where the final feedback was coming from a speed of light model at the very bottom, that is where the latency comes from. So once you complete the iteration, at the end of the final iteration, you can compute the difference in latency compared to the previous iteration, and that becomes the latency reward. But during the course of performing mapping node by node, we don't have that latency feedback available immediately. So we come up with a proxy by using what we call a congestion metric. Now, this is basically when you have nodes assigned and there are resource dependencies, node dependencies, meaning the output of a computational op is going to be the input to another op. How long of a distance does that tensor have to travel? And how contended is that channel going to be? That is the proxy of congestion that we take into account. And this is something which we can heuristically compute and apply every iteration, even when we don't have feedback coming directly from the speed of light model. Next slide. Click one more time. Okay. Here, for example, we have illustrations of how this the training progresses. On the bottom, we have two graphs which show the reward, the growth of the reward function in two different scenarios. The graph on the right-hand side is, bottom right, is a little bit more interesting because it shows periods of no improvement in the net reward, followed by periods where it does find a better optima and converges towards a higher reward. It may not be very easily readable, but on the same bottom right graph, you can see some gray dots. Those are places where the agent explores points in the search space where the reward was actually lower than the best known at that time. So that does not affect the agent's ability to converge to the reward. It simply takes that as a feedback and learns over time that those are not good decisions to take. On the top right, you have a slight representation of two different types of rewards that we talked about. And we found that direct assignment is a little better compared to swapping action, especially if we are talking about large neighborhood in terms of how long it takes to converge. you can imagine that if your action is constrained by just swapping between north, south, east, west neighbors in a small neighborhood, it will take much longer for that agent to find the optima or explore the solution space comprehensively, as opposed to if it has flexibility of any assignment and given enough time, that we believe is the better action strategy. Next slide. One more. All right. We have a few results. We can ignore some of the details on the left-hand side, but focus on the bottom left. Here, for example, we trained a model on one of the BERT models. These are 4 different variations of the same architecture, which I'm sure most of us are familiar with. We trained it on a BERT medium, and then we applied that same model on 4 different variations of BERT, which differ in terms of the number of layers, the number of attention heads, and so on. And you can see that compared to the default heuristic-based mapper, which is on the middle column, the SOL numbers, the latency for at the end of the agent's assignment is always less. The one place where you may question why is the number not bigger is on the BERT large case, and that's because the SOL internal mapper is highly tuned for or highly suitable for BERT large. So it's a harder problem to get past. It's already very well optimized, but the agent is still able to find a slightly better mapping, which results in lower overall latency. Last slide, previous slide. So in terms of next steps, these are some of the initial results. These are very promising. The things that we want to explore next is how can we apply this on even bigger problems, so larger models. We want to investigate the generalizability, both in terms of graph representation and training it on one type of network and applying inference on another. And also, we want to take this same kind of concept and formulation and apply it to the problem of graph partitioning. Okay, I'll stop here.
Okay. So Ilya, you want to cover this?
Yeah, sure. Yeah, so in this kind of final remarks, we wanted to say a few words about our current research directions and possible collaborations and future work. So the first bullet here is what we call pattern exploitation. So here we can talk about sparsity and outliers separately or sometimes together in 2 modes, structured and unstructured. And for to the different modes, we have different approaches. For example, as we already saw, the idea of GPTQ together with the sparsity can be applied in the unstructured case. So here we can both do the GPTQ error propagation and also find places where we can, let's say, completely remove the weights and leave only zeros. Another approach is to, for example, outliers. If we know that the structures of outliers are unpredictable, then we, for example, may decompose our matrices into sums of some dense matrices with, let's say, bounded weights, plus some very sparse matrices that will contain our outliers. So here there are also a few trade-offs related to raising the compute, but maybe significantly improving the accuracy. In the structured case, for example, for structured sparsity, we have specific formats where we can, in hardware, account for those sparsity patterns and make the compute much faster. For structured outliers, there are a few approaches. One of them is, for example, the SmoothQuant paper, where the idea is to carry some of the kind of computational like accuracy problems that are emerging in the weights to some accuracy problems emerging in activations. We want to carry them into weights. For example, when we see the specific patterns of outliers, or like very large values appearing in, for example, rows of activations, we can carry those to changing the weights, and this way kind of regularizing the weights of the activations. Another idea is what we call a transpose blocking. So here, as you saw in the previous slides, when we need to multiply two matrices, we have to quantize them in a very specific way. The first operand has to be quantized row-wise, while the second one has to be quantized column-wise. If we see specific patterns in the outliers and activations of the weights, we might want to change these directions of quantization and, for example, quantize the activation instead of row-wise, column-wise. This way, the outliers will not ruin the accuracy of some other smaller values. So we're exploring a few directions here as well. Now, there have been some kind of recent interest in developing and exploiting new formats. And here we're also comparing our BFP to some other emerging formats. For example, the recently reported MX format, where we have kind of two stages of exponents, like two exponents are applied for a larger block, and then you have smaller blocks with their private exponents. So we are comparing BFP to those formats and are waiting modifications to BFP as well. Yeah, Satyam, do you want to talk about mapping?
Sure. As we mentioned, we have a few research directions that we are currently exploring about larger graph embeddings, applying different techniques for state space representation to apply RL for partitioning. We're also looking at potentially applying the RL problem on graphs in spectral domain. So those are all of the different areas in which the initial findings of our RL effort on the mapper problem have given us some directions for further research.
Okay, so we'll stop here and into the Q&A.
Thank you. Yeah, thank you for a great talk. I will take the chance right now to invite you all to the next speakers happening in 2 weeks on the 30th of March. We'll host Karen Bergman from Columbia University, and she will talk about realizing petabits per second I/O and sub-picojoule per bit system-wide communication with silicon photonics. So now let's go to the Q&A session. And in the Q&A session, there are 2 ways you can ask questions. Either please raise hand, and then I will unmute you, or please put the question in the chat, and then I'll read. So I can see already that we have a couple of people asking. Let me start with Saleh.
Hi, can you hear me?
Yep.
Okay. Thank you for the talk and great work. So basically, as you mentioned, for this using GPTQ with this PFP format, you mentioned that you use this block size of 64. And I'm wondering if you have studied different block size and its effect on the accuracy with this block format. Because when we work on this GPTQ paper, we studied the integer with group-wise quantization. And then we found that actually using a smaller group doesn't help us too much to improve the accuracy. And I'm wondering if you have done such kind of study and with block format type.
Yeah, thank you for the question. Yeah, we did study it, but mostly for those block sizes that are easily supported by our hardware, which are, for example, 128, 64, and maybe 32 and 16. And indeed, the kind of improvement with smaller block size is not very significant. So yeah, that's why we decided that, for example, stopping at 64 block size is already good enough.
But by the way, just to add, guys, on the block size impact, so there is some impact that, I mean, it's about 1 dB in SNR improvement for doubling the block size, at least for block sizes in the range, up to about 128. That's just a rough rule of thumb. So there is some improvement, but obviously it's much less than like just increasing your Mantissa bit by 1, which is 6 dB in SNR.
But just a small comment to what Ilya says. Yeah, so when we are talking about let's say accuracy of those specific layers, then it is approximately 2 dB, like for doubling the block size. But when we are looking at the kind of influence on the overall perplexity, let's say overall performance, then this overall perplexity kind of stabilizes pretty well, even for larger block sizes. It improves, but we are already within a very low kind of margin with, let's say, 64, 1.8.
Thank you.
Okay, then we have Timo.
Yes, I would be interested to know a little bit more about how you obtain the initial graph that you then proceed to map. Can you hear me?
You mean you're asking about the initial graph that we were using
of operations? So is this already static and using only a specific input size, or do you have some formulation for this so that this can accommodate varying input sizes?
Yeah, it does accommodate different input sizes. This is coming from the upper layers of our compiler. So you take standard models, take it through a series of transformations, and that results in the representation that get fed into the initial stages of the mapper. Another thing which probably may be related is that the initialization of the assignment is mostly random. So you assign any resources and then let the agent figure out what the right strategy should be.
Is this documented somewhere? This kind of
this is in actually one of the papers. If you go to slide 30 for just a second, it has the name of our paper, which was published, which was recently presented at the EMC2 workshop last month.
Thank you.
You can find it in archive, right, Satya?
Yes.
I have a follow-up question, actually. So you mentioned that you also represent resource dependencies as edges, right? What kind of resource were you considering here?
Let's suppose you have a matrix multiplication engine. If you have two completely independent matrix multiplications in a graph, but you want to use them using the same matrix engine, those would become explicit resource dependencies, even though they were implicit in the original graph.
Okay, thank you. Okay, we also have Patrick.
Yes, thanks a lot for the very interesting talk. I have a question about the chiplet architecture. So there are multiple technologies to build these chiplet architectures. There are organic package substrates, there are silicon interposers, both passive ones with only wires or active ones with wires and transistors. And my question is, which technology did you use and why did you decide to use the given technology?
Yeah, we used an organic substrate and passive interposer. And we compared this against other interposers, RDL-based or silicon interposers. We find that the option that has the sort of the lowest cost is, and also no size constraints, are these organic substrates. Most silicon interposers have reticle size limits, and beyond the use of integrating HBM on microbumps on silicon interposers, there isn't much of a use case for something like this, where we are trying to scale up and break the monolithic limits. Whereas organic substrates are well understood. They're sort of traditional MCM packages. People can actually build today 100 millimeter by 100 millimeter substrates, whereas in silicon interposers, it's a small fraction of that. So hopefully that answers your question.
Yes. Yes, that answers it. Thanks a lot. Very interesting.
Okay, and then we have Maciej.
Hello. So I have a question about your workload. So you mentioned language models like BERT as the main use cases. Have you guys thought about also targeting more irregular and sparser things like graph neural networks, graph attention networks? And if yes, do you have any specific plans or comments on this?
We have been concentrating on language models like generative language models. Both transformer encoder decoders. We also it's a generic programmable architecture. So we do support things like stable diffusion and most popular neural net types. We haven't specifically focused on graph neural nets yet, but a wide variety of convolutions, transformers, encoders, decoders, specifically generative models is where our current focus is.
Okay, thanks.
Great. I don't think there are any other questions. At least I don't see any other questions. So thank you again for a great presentation and great work to all of you. Thank you also everyone for joining us, and I hope to see you all in 2 weeks.
Thank you.
Thank you very much for hosting us. Thank you.
Thanks.